Okay, it's officially 4 o'clock. I'm sure there will be more people that come on in. Welcome. So this is our Eugene Parker Lecture. It's an award that Space Physics and Astronomy gives out every 2 out of 3 years. And this year, where, as you can see here, our award winner, of course, is Peggy Shea. And she will be introduced by Dan Baker.
Thank you and good afternoon. Margaret Ann Shea, I just advanced her slide. Margaret Ann Shea, universally known as Peggy, began her research career as a graduate student at the University of New Hampshire. She was the first woman to receive an advanced degree in physics from UNH. After brief positions at the University of Hawaii and Avco Corporation, she joined the Air Force Cambridge Research Laboratory, which became the Air Force Geophysical Laboratory, and later the Air Force Research Laboratory. At Hanscom Air Force Base in Massachusetts, Peggy worked with the Air Force until her retirement from federal service. Her research concentrated on cosmic radiation and solar terrestrial phenomena. Peggy is recognized as a world expert on geomagnetic cutoff properties for cosmic rays and many other things. Peggy's been active in finding and preserving unique historical scientific records, and she has devoted much time and effort to bridging the scientific and engineering communities and the gap between them. While she is now retired from the Federal Civil Service, she has emeritus positions at the Air Force Research Laboratory and is an adjunct professor at the University of Alabama in Huntsville. Peggy not only has had a remarkable personal research career, but she has also expended an enormous amount of energy enabling the research of others, especially within the international community. Not only is she an amazing writer, authoring or co-authoring over 400 papers, but she's also a prodigious facilitator, editing some 46 major reports, proceedings, and scientific books. Moreover, even though she has spent most of her career doing basic research for the U.S. Air Force, she has worked tirelessly with international organizations such as SCOSTEP and COSPAR. I can say, having benefited from Peggy's tutelage in space research and space weather in particular, I can attest to her influence on generations of space researchers around the world. Obviously, Peggy has been active on both the national and international scenes, realizing that solutions to global problems require worldwide cooperation. Peggy has worked with countless U.S. scientists, including her husband Don Smart, who is here with us today, but has also worked extensively with scientists from Eastern European countries long before it was the thing to do. Her international activities have been recognized by a medal from the Soviet Union Academy of Sciences and also by foreign associateship of the Royal Astronomical Society. In addition, Peggy is a member of the International Academy of Astronautics and a fellow of the AGU. She's the past recipient of the AGU Waldo Smith Medal, the COSPAR Distinguished Service Medal, and the Distinguished Alumni Award at the University of New Hampshire. In addition, Peggy has received several Air Force awards, such as the Scientific Achievement Award, the Air Force Association Citation of Honor, and the Gunter Lesser Memorial Award for outstanding career contributions to scientific research. Peggy emphasizes when talking with her that she's not all about work. She's an accomplished needlepoint artist. She also enjoys reading, nature photography, snorkeling, and gardening. But clearly, Peggy is first and foremost an exceptional scientist and a great member of the solar terrestrial community. It's my honor and privilege to introduce Peggy Shea as a 2019 Parker Lecturer speaking on A Scientist's Adventure in Space Weather from IGY to the present. Please join me in welcoming Peggy Shea.
Well, thank you, Dan, and Madam Chairman and fellow physicists. Space weather effects have been present for decades. Little did two telegraph operators, we'll get it. Little did two telegraph operators using auroral currents to transmit their messages in September 1859 realize that this phenomena would be called a space weather event more than a century later, and that was the well-known Carrington event. Similarly, the discovery of solar radio waves by John Hay was the result of interference on coastal radar in February 1942, another space weather effect. That was also the first recorded ground-level event as recorded by ionization chambers of Scott Forbush. The term space weather was not in the scientific vocabulary when I graduated from high school. This talk is essentially my story of how a young girl from a small town in a small state had an adventurous career in what eventually became known as space weather. I had just turned 17 when I enrolled as a freshman in the College of Technology at the University of New Hampshire. During freshman week, I was called to the dean's office when Dean Shealy suggested that I might want to switch from technology to liberal arts because physics was difficult. I declined that suggestion. But a week later, I was back in the dean's office, not to accept his suggestion, but to register a complaint. The instructor of my engineering drawing class had insulted the two girls in the class with his opening statement. "Well, boys, we have two girls in this class. How quickly can we get them out?" There were 3 girls who had enrolled in the College of Technology when I was there as a freshman. I was the only one of the 3 to graduate with a college degree from the College of Technology. In my sophomore year, I was hired as a data clerk on an Air Force-funded cosmic ray research project. The physics department had operated 2 neutron monitors. One was located in a truck on the campus, shown on the left, and the other was at on the summit of Mount Washington in New Hampshire. The cosmic ray intensity was recorded by mechanical registers, which were registered by film every 15 minutes. At the end of each week, the film was removed and developed. My initial job was to sit in a darkened room, write down the numbers of the film strip, and since they were cumulative, I had to do the counting rate on a calculator. And the calculator we had was a hand calculator, called a Marchant mechanical machine, and it was very big. It sat on the desk, and it made a lot of noise as we did it. We didn't have these nice fancy little things that came along 25 years later. I retained this job until I graduated. With the advent of the International Geophysical Year in July 1957, followed by Sputnik a few months later, a career in space physics seemed to be a definite possibility. The establishment of the World Data Centers enabled data to be much more easily obtained from a large number of geophysical detectors all over the world. We submitted bi-hourly data from the Mount Washington Neutron Monitor every month to data depositories in the United States, Japan, Sweden, Belgium, and the Soviet Union. If we had a request for something of, say, a Forbush decrease, and it was small time interval, it was all done by hand, pencil and paper, and by mail. No email in those days. I obtained a research assistantship at UNH for graduate work and continuing to work on Air Force-funded cosmic radiation project. Having completed my coursework for the MS degree in 1960, I needed to do a master's thesis, which was a requirement at the University of New Hampshire at that time. Fortuitously, the relativistic solar proton events of November 1960 was the perfect subject. The problem was to get the necessary data down from Mount Washington in a timely manner. The ride to the top of Mount Washington on the Mount Washington Auto Road, and it was really icy, in a canvas-covered Jeep to recover the data was an adventure I would not want to repeat. The wind was blowing at 90 miles an hour. I'm in a canvas-covered Jeep, remember, and the temperature was 20 degrees Fahrenheit. Not exactly a picnic, but it certainly allowed for some wonderful photography when I was at the summit. At the same time, 1960, I met the two scientists who played the most important roles in my career. The first scientist was the contract monitor for the Air Force contract with UNH that was paying for my assistantship. The other was Dr. Kenneth McCracken, an Australian who had a postdoc position at MIT, and many of you may have heard about Ken McCracken. Ken had been working on a digital computer program to trace cosmic ray trajectories in a model of the geomagnetic field. And he had use of the MIT computer for his calculations. This state-of-the-art technique opened up many possibilities for getting a better solution to the cosmic ray cutoff rigidity problem, and to also determine the direction and position in space of solar particles impacting the geomagnetic field. The equations for charged particle motion in a magnetic field expand out to 3 partial differential equations with 6 unknowns. Ken used his computer program to determine the anisotropy of solar particle events. And I promise you that is the last equation you're going to see in this talk. Here is an example of cosmic ray trajectories in a model of the geomagnetic field. We actually, since the particles coming in are protons, we do electrons with the same rigidity, and we trace them out from the position on the Earth out until they reach the end of the, well, primarily the magnetosphere boundary nowadays. The higher energy particles go right out as shown by the numbers 1, 2, and 3. And as the energy decreases, the effect of the geomagnetic bending of the geomagnetic field, these particles start to work around the geomagnetic field. And they eventually will come down and often hit the Earth or the top of the atmosphere, which is what we had used, the top of the atmosphere we call 20 kilometers. That causes something called the cosmic ray penumbra. And so we have some that go out very quickly, some that are not allowed, and then at the very end, at the very bottom, we have those that are completely not allowed. Those are the lower rigidities. So it's a very time-consuming position. Just as I was completing my thesis work, I had another rude awakening. Dr. James Van Allen was hosting a small cosmic ray workshop at the University of Iowa. The results of my thesis were to be presented at that workshop. However, another graduate student was selected to present that paper with he as a co-author. When I objected to this action, I was told that this graduate student was selected because fellows go further than girls. Nevertheless, I finally swallowed my pride and received my MS degree. I stayed at UNH another year, continuing my interest in the cosmic ray trajectory program. The Air Force contract monitor continued his interest in this subject and arranged for the use of the Air Force Space Track computer for additional calculations. I subsequently joined, as Dan said, the Air Force Cambridge Research Center in November 1964 and continued my research on geomagnetic cutoff rigidities. Several groups were conducting cosmic ray latitude surveys during solar minimum and were trying to find the knee of the latitude curve. And as you can see here, this was a Sawyer voyage done by the Japanese. In using the cosmic ray counting rate on their latitude survey and the dipole magnetic field, they approximated the cutoff of the knee would be somewhere around 6 GV. Quimby and Wenck, at that time, British scientists, had an empirical method, and they estimated that the cutoff rigidity would be between 5 and 6 of the knee. And there was Project Magnet at the same time that had it even lower than that. So there was definitely some confusion as to where the knee of the latitude curve was. In addition to that, there were inconsistencies in the increases observed by neutron monitors during relativistic solar proton events, and particularly when they were audited by the presumed cutoff rigidity of the station that was monitoring it, usually by neutron monitors. The use of the cosmic ray trajectory program seemed the most logical way to resolve some of these discrepancies. Whoops. Now, the concept of charged particle tracing in a magnetic field model, as you can see, this one's a particle that goes right straight out, but the geomagnetic cutoff rigidity value for a specific location and a direction is a function of the geographic latitude and longitude, the altitude, the local time, and geomagnetic conditions. It's not particularly a clear-cut solution and takes a lot of time. In those days, it took a lot of time on the computer. The tracing of charged particles in a numerical model of the geomagnetic field is computer time intensive, so much so that we developed the concept of computer years required for a world grid of cutoff rigidity calculations. With a high degree of interest in this problem in the scientific community, we started using computers in different locations: Los Alamos, Lawrence Radiation Laboratory, and the Pentagon, as well as at the Air Force. The technique for calculating cutoff rigidities was published in JGR in 1965. The technique was the fundamental technique, and it is still used today for calculating cutoff rigidities, although the models, of course, have changed. The technique has not. We'll go back to the Sawyer data here. Whoops. Here we are. When we used the new values of cutoff rigidity that we had calculated for the Sawyer data, you will see that the knee of the latitude curve was definitely much lower and much more in agreement with the Project Magnet that had done a worldwide survey. So we felt that we were certainly on the right road. Get it yet. The concept was, at the same time that all this happened, I presented a paper in the 1965 AGU meeting proposing an analytical method to analyze solar flare-associated cosmic ray increases, that whole technique was initially met with some skepticism, and one member of the audience came to me afterward and just smiled and said it'll never work. Well, it was skeptical. I thought it might give it a try. The concept was that asymptotic cones you could use an asymptotic cone of the particles of a neutron monitor, and as the particles would fall along the field lines, then if your neutron monitor was looking in that direction, you would see the highest increase versus a station located down here at B. Didn't get that yet. Would not receive the same high increase. Of course, a lot has to do with anisotropy and scattering in the interplanetary medium. Anyway, this became eventually the standard technique to analyze relativistic solar particle events. Again, it is a fundamental technique. Now we'll switch a little bit. In early 1966, Dr. Hugh Carmichael of Canada, the Canadian Atomic Energy Laboratory, asked if we knew of any location in the United States where he could put his mobile monitor to record the cosmic ray intensity, both close to sea level, at a mountain elevation, and also at a high geomagnetic cutoff rigidity. And his latitude survey that he had done was the first one, which went all the way down from Canada along the east coast down to Acapulco, Mexico, and then up through the center part of the United States. The obvious choice to me at that time was Haleakala on the island of Maui. So we then had another latitude survey that went all the way along the west coast, and then eventually we moved the equipment out to Maui. He had a 3-tube neutron monitor on a mobile van, and that was how we transported it from one end to the other. Within 3 months, we had mounted a campaign that included the entire West Coast after we transported the monitor to Maui. I was the U.S. scientist in charge of the field trip. In addition to various monitoring locations along the western part of the United States, we were able to involve the Los Alamos Flying Laboratory, which had a small neutron monitor on board in this project. And at Mount Palomar, you can just barely see the contrails of the KC-135 right up through there as they flew at altitudes 40,000 feet to get both an altitude survey at the same time that we had a ground survey. They also did the same at Mount Hood in Oregon. Once we got to Hawaii, and there's a different type of volcano, that's a different type of mountain than the Mount Hood, we had to have a police escort to travel the one-lane, two-way road to the summit of Haleakala. When we were in position at 10,000 feet, we coordinated again with the Los Alamos group, who organized a flight around Haleakala at 10,000 feet. So we were able to intercalibrate the one at 10,000 feet on the mountain with the one with the airport going it all the way around us. And it was really funny because we had a theodolite looking at them, and they, on the radio talkie back and forth, and they would say, how are we doing? And I would say, drop it down about 100 feet or so. And after the second time around, I asked them to drop it down another 100 feet, and they said they did. And we lined it up, and I said, about 50 feet. They said, forget it. And there they are up at 40,000 feet when they went all the way up. So we had measurements from sea level on Maui at different elevations up Haleakala, and then a calibration at 10,000 feet, and then the aircraft did different elevations all the way up to 40,000 feet. That ended up in a series of, both latitude surveys, a series of several papers, primarily in the Canadian Journal of Physics, because it was a Canadian experiment. Now, 1966 was an extremely busy year. I had 3 AGU presentations, an APS presentation, 2 workshop presentations, latitude surveys in May and June and July, and some presentations in Yugoslavia, invited speakers, and so forth. Before I go into that, I am going to mention one other thing here, because I missed one point that I did want to mention. The first time we published any of the cutoff rigidities for a partial world grid, this was over South America. I was invited to go down and present it at the COSPAR meeting in South America, which was in Argentina. There it is. That was in 1965. When I was down in Argentina, I was also asked to go to Bolivia to give a talk at the University of San Andres. Now, what I didn't anticipate was when I went to Bolivia, they were in the middle of an insurrection. There was curfew in place. We could not go out in the streets after 10 o'clock at night, and we couldn't go until 6 in the morning. They were shooting it up, and the power supply, one of the power supplies to the university, was blown up the morning I was to give my talk. I did not expect that an adventure in space physics would lead to that type of an adventure in South America. Back to activities in 1966. It was a very busy year, as you can see, and I was also a co-author of 4 publications. We were still working on this. Now, do you remember earlier I mentioned the 2 scientists who made the most impact on my scientific life? One was the Air Force contract manager on the Air Force contract when I was in graduate school. Well, by now you know that was Don Smart. Don proposed, and we even had time for a proper wedding, which was followed by a honeymoon that included stops at Los Alamos, the Air Force group at Cheyenne Mountain, ESA in Boulder, Colorado, and the Lawrence Radiation Laboratory in California, where we were using computers again. And what else would you expect of two physicists? The first grid of trajectory-derived geomagnetic cutoff rigidities using the 1955 epoch of the geomagnetic field was published in 1967 and consisted of 264 specific locations around the world. It took 3 years to do that set of calculations. Eventually, we were able to produce an isorigidity contour map of cutoff rigidities around the world. Now, at this point, I'm going to divide the talk into two separate threads: geomagnetic cutoff rigidities and solar proton events. Throughout the next few years, we continued our work on geomagnetic cutoff rigidities. With increasing satellite data, there were different models of the geomagnetic field becoming available. In subsequent research, we found that there was a rapid decrease in the vertical cutoff rigidity for stations in Huancayo, Chacatayo, Aguilar, all over the South American area between 1955 and 1975. We didn't know at the time if this was a problem with the geomagnetic field or there was some problem, other problem that we did not understand. Maybe it was the new models that were coming out. We predicted, though, that a stable neutron monitor in that region would have an apparent increase in cosmic radiation over that same time period. Again, some people were a little skeptical of this. However, John Simpson, using the Huancayo, Peru neutron monitor measurements from 1955 into 1975, saw that the cosmic ray intensity did have an increase, steady increase from solar minimum to solar minimum, whereas the corrected values, when he corrected them, showed a different different aspect. Now, he checked it with other high latitude equatorial stations such as Mount Nurakura. They did not show this, so they knew it was a change in the cutoff rigidity. Also, it was not seen in John Simpson's monitor in Climax, Colorado, because the cutoff rigidity did not change with time there. The effect of the secular variations in the geomagnetic field was much more apparent when the South Africans flew a neutron monitor on board a plane from Johannesburg to New York City. And they said that when they had an equal counting rate, they could not get the same cutoff rigidity, and they had a very large discrepancy, as shown right here. What we ended up doing was taking their data and doing the calculations for the exact locations that they had done that, using the models appropriate for the actual month of the airplane flight. And when we did that, we had a convergence of the two curves. This did tell us that the variations in the geomagnetic secular field were very real. And in some areas of the world, we found that there was as much as 1% per year. This means that for precise cosmic ray measurements, you must consider the secular variations. The secular variation of the geomagnetic field was not the only aspect of changes in the geomagnetic cutoff rigidity values, as there was a daily variation. It was identified in balloon data from Fort Churchill. And here you have, utilizing a magnetospheric model developed by Williams and Mead, we were able to calculate the changes in the cutoff value as a function of local time. And you can see that the diagonals there are the measured cutoffs, the calculated ones are the dots, and those were the measurements of that was the electrons that they were using, but it also worked for the protons. Later, we found that we did a upper latitude survey. We found that the daily variation is much more prominent in the polar regions than at mid-latitudes. Now I'll switch to the solar proton work that we did. Since my master's thesis was about solar protons, I continued to study these events by using extensive databases. I was asked to publish my initial ground level event data in a cosmic ray conference publication, and that resulted in the current GLE numbering system, and for all those that don't like that numbering system, you can blame me. This database for relativistic solar cosmic ray events is maintained now by the University of Oulu. Another task involved the derivation of the correspondence between polar cap absorption events and proton flux equivalent. These initial tables were included in a catalog of solar particle events from 1955 to 1969, and we did our very best to do what we could with what we had for the IGY time period and before space measurements became available. And this was also summarized in a document on solar terrestrial physics and meteorology, and that was published by the National Academy of Sciences. As satellite data became available, the Proton event database was extended to lower energies as the Air Force was concerned about polar communications. The database for 218 solar proton events detected at the Earth for 3 solar cycles was eventually published in Solar Physics in 1990. Now here are the basic characteristics of a solar proton event. One of our Air Force assignments was to predict the characteristics of solar proton events. They wanted the start time, the time and maximum intensity, and the duration of the event with an accuracy that you just don't want to talk about, because in those days we just didn't have it. Our initial knowledge of the solar proton events in 1967 was very, very limited. Most events appeared to be from the solar activity on the western hemisphere of the sun. Continued extension of the solar proton database that we were working on allowed us to organize the data using the interplanetary magnetic field, which produced some order to the chaotic mess. This led to a relatively crude solar proton prediction system that was initially implemented by the U.S. Air Force. Now, this was an absolutely fascinating time to be a scientist in the space physics community, as many international organizations were conducting studies and workshops on solar and interplanetary phenomena. We were fortunate enough to be able to participate in many of these, and we visited several observatories, such as the Udaipur Solar Telescope in India, the Radio Telescope in Australia, the Lake Baikal Solar Telescope in the Soviet Union, and a solar telescope in Kunming, China, and Eugene Parker was also with us on the trip to China. Most of the presentations that were given at all of these meetings all presented new and exciting research, and there was a large number of publications that came out from almost every one of the meetings. You'd have at least one publication, and everything was bright and new in those days. However, as our knowledge increased, so did the complexity of our roadmap. We had many more things to worry about in trying to predict solar proton events. And we also had a massive solar terrestrial puzzle to assemble. In early August 1942, the sun produced the first extreme solar terrestrial event of the space era. The assembly of spacecraft and ground-based data was assembled in 4 publications from World Data Center A. This event is still studied today, as documented by Dolores Knipp and colleagues in a recent Space Weather article. We also learned of unexpected groups that were affected by large geomagnetic storms, such as the homing pigeon community in Europe and the United States. The pigeons fly by the magnetic field when they go from place to place, and the geomagnetic field disrupts their mode of flying. And so for those people that have their pigeon races, this was a very serious situation. They were asking the forecasting centers, please, to predict when there would be major geomagnetic storms. Throughout this time period, the space community became aware that our assets on ground and in space were increasingly more vulnerable to space and geophysical environment. The first solar terrestrial prediction workshop was hosted by the Boulder Environmental Research Laboratory in an effort to delineate areas where it would be possible to predict rapid changes in the space environment. And out of those prediction workshops and other activities that were going at the same time, the term space weather was developed. Sorry about that. Now, during a major geomagnetic storm in 1986, two trains collided in Canada. The question arose as to whether the geomagnetic-induced currents could have interfered with the switching signals, but an official inquiry revealed that the signal equipment was properly grounded. GCRs have previously been attributed to anomalies in the northern railways in Russia, including an incident in March 1989 during the same active period when Quebec, Canada lost the electrical power for the entire province of Quebec. Some people may recall the two Canadian communication satellites, Anik 1 and Anik 2, that tumbled out of control in January 1994. The operation of one spacecraft was quickly recovered, but recovery of the second spacecraft took several months. Sporting events have also been affected. During the 1994 Olympic Games, the BS-3A satellite suffered an electrostatic discharge just as Japan's Masahiko Harada was jumping for the ski jumping team's championship. The outage lasted 60 minutes. It was joked that a miniature earthquake occurred in Japan as people jumped to adjust their TV sets. Several other anomalies started to be identified. Particle energy deposition in solid-state detectors can change the state of a device, resulting in unexpected command functions. You don't want those little devils into your detector. Galactic cosmic radiation can interfere with the pointing systems on star sensors, such as the Hubble telescope. While these type of events received a fair amount of publicity, less noteworthy anomalies occur daily. Thus, it is essential we try to predict the status of the environment through which these electronic systems operate. One of our assignments was to present lectures on the variability of the space environment to design engineers. We quickly learned that engineers and space equipment designers are not interested in the language of scientific researchers. Their eyes just completely glaze over when using words such as coronal mass ejections, heliospheric current sheets, recombination coefficients. Forget it, they don't care. But their eyes will light up when presented with numbers giving the ranges of energetic particles and magnitudes of events as a function of a location in space. Those are the numbers that they need to design the instruments which will be flying in space. This work brought us then to the problem of space radiation for aircraft crews and astronauts, and how our work on geomagnetic cutoff rigidities and solar proton events tied into the new discipline of space weather. The community had long known that during a large geomagnetic storm, the auroral oval moved equatorward, thus allowing particles of lower energies into the atmosphere at latitudes inaccessible to those energies under quiescent conditions. This translates into a lowering of the geomagnetic cutoff values at those locations. And if there is a coincident solar proton event at the same time, those solar particles have access now to latitudes which they previously could not reach. So we started working on the radiation dose of concern for astronauts, particularly for during long-duration space missions. It's a very minor concern for commercial flights. It's not a showstopper, but the question does come up as to what does it do to your DNA? The large solar proton events of the 23rd solar cycle did tie this all together. In August 1989, the space shuttle was in orbit during the initial part of an energetic solar particle event. In October 1989, a series of large energetic solar proton events and subsequent geomagnetic storms occurred over a period of 6 days. At the same time, the Cosmic Radiation Environment and Activation Monitor recorded the cosmic ray environment while on board the Concorde aircraft flying between France and the United States. These and other events led to the inevitable question how to estimate particle access to the space station and to aircraft routes during disturbed conditions to ascertain the radiation exposure. While there have been various mathematical models of a disturbed magnetosphere developed between 1965 and the start of the 23rd solar cycle, The Cheganenko models provided the necessary tools to determine the cutoff rigidity of a specific location as a function of day, season of year, and geomagnetic conditions. Using a 1995 internal geomagnetic field model combined with a 1989 Cheganenko magnetospheric model and 3,000 hours on a IBM supercomputer, we calculated a world grid of cutoff rigidity values for the space station as a function of universal time and geomagnetic conditions, a total of 604,000 vertical geomagnetic cutoff values, and NASA is currently using those values for their work. To determine the accuracy and value of these calculations, the Space Radiation Group at NASA's Johnson Space Flight Center found excellent agreement between their measured radiation dose during the solar proton event experienced in August 1989 and the radiation dose predicted using the known solar particle flux and our cutoff rigidity values appropriate for the time of event. These calculations were made for the space shuttle orbit during the first few hours of the solar proton event. And on this slide, our calculations are the black line, and the actual values that they had of the space radiation is the green dots, and they were taken every minute during that time period. On August 13. It was just before they landed. The event was still in progress when the shuttle came down. These cutoff rigidity values were also used as an evaluation of the radiation dose on the Concorde and other aircraft flights during large solar proton events, such as the Halloween event, which I mentioned earlier. Many of the space weather events in the 23rd solar cycle have been documented in this publication in Space Science Reviews. As it turns out, the 24th solar cycle is now just finishing, and it has had a deficiency of large solar terrestrial events. And I'm hoping that the predictions, as much as I respect the values that they have in NOAA for their new sunspot number, I really kind of hope that they will give us a couple of really good events to be able to work on for the 25th solar cycle. But now we go to the future. Now, these types of satellites are very much a work in progress. As our technology advances, both on the ground and in space, and as humans continue to work on the space station or future platforms that will be in space, a knowledge of the spatial environment is essential to protect both humans and the electronic devices upon which the humans depend. While considerable progress has been made in the last 50 years, there is much more to be done. While we undoubtedly learn from the detailed studies of each and every major space weather event, in my opinion, it is better to start with a broad-based solution to each problem that can be refined as our knowledge increases. However, when the solution becomes so complex that it exceeds the threshold of financial pain, it is time to reassess our priorities. Now, to the young scientists in the audience, I would recommend that you set goals for yourself and follow your dreams. That's what I did. Your goals will change with time, but always keep a goal toward which you are working. Don't be afraid of hard work. Treat others with respect, and always give credit to those who deserve it. Finally, some of you know that I have quoted Robert Frost's poem, The Road Not Taken, in previous talks. The last two lines essentially describe my life from the time I entered college to the present. Two roads diverged in a wood, and I took the one less traveled by, and that has made all the difference. There were times in my career when I hit stormy weather. There were frequently bumps in the road. But I had many times with a clear and steady path toward a specific goal. And as for my future, my husband and I still hope for a few more years exploring the spatial environment. And thank you for listening. Is that what you wanted?
So we have time to take a few questions, if you have questions for Peggy.
It was completely misunderstood.
So, is that top level radiation at the location, for example, of the South Atlantic anomaly of the inner radiation belts? Has anybody looked at, are there any mutations or enhanced cancer rates at the South America in the regions that are close to South Atlantic anomaly?
Well, I know that the radiation belts have been changing.
Repeat the question for everybody,
Okay.
they can't hear.
I didn't quite get the entire question.
Wants to know if there's increases in cancer rates and stuff of people that are close to the South American anomaly.
That I don't know. I don't know anything about the medical records, but I do know that the South American anomaly has been moving to the west, and that the cutoff rigidities are changing there. And regarding to your question, has there been any increase in the cancer rates? That I just don't know.
So I just had a comment. I wanted to thank you for enduring the treatment that you did early on in your career so that you paved the way for female scientists in the future like myself to endure a much less hostile environment. So thank you for doing that and being strong through that whole experience. Appreciate it.
Well, thank you. Thank you very much for that comment. I must say, probably the lowest point was when my thesis was given to somebody else to present at a scientific meeting with his name on it. I'm Irish, and I must admit I kind of lost my temper.
Any other comments or questions?
One way in the back there.
Is Andy over here? Is Andy over here?
We talked about the Bolivia situation. The 1965,
Andy, can you stand up and speak a little louder?
1965 COSPAR meeting was moved from Buenos Aires to Mar del Plata in the last minute because of student riot.
Yes. What Andy was saying, that the 1965 COSPAR meeting was originally scheduled to be in Buenos Aires. There were student riots at the University of Buenos Aires, and so the cold conference was moved to Mar del Plata in Argentina, where I remember, one, it was very cold, and two, because it was wintertime there, and two, there were armed guards outside the hotel the entire time we were there. So you're right, I do remember that.
There's another
A question over
Bill.
there.
Very nice talk, Margaret. I was wondering if you could comment on looking towards the future, the desirability of maintaining a network of neutron monitors for space weather.
Well, the question is, do I have a comment about the desirability of having neutron monitors for the use of space weather? Being a neutron monitor person from the start of my career, I absolutely agree we should have a network of stations, preferably in the higher latitude regions, but one of the main reasons is to determine something about the anisotropy of the relativistic solar proton events, which has really been very interesting for many of us in the cosmic ray community. That would be useful for the space weather community, but those would only detect the extremely high energy particle events. There are, up until the 24th solar cycle, there were about 15 of these per solar cycle. The 24th cycle only has had 2. But I do think that we should have it there for other good scientific reasons too. A network of maybe 6 or 8 in the northern polar regions, equally spaced around the world as best you can do, because you have to have logistical support, I think would be very, very valuable.
And we have a question from Dolores over here.
As a comment, Peggy, I just wanted to thank you and Dawn for all of the help that you have provided in the corporate memory for telling some of the war stories that have come out in the last few years. Without your help, I don't think we would know what true extreme space weather is. So thank you to you and Dawn both.
Well, thank you very much, and since
I'll bring it up here.
And I think it is about time now for me to introduce the one man who has made the most influence in my life, my husband of 53 years, Don Smart, and my coworker.
And I've enjoyed it very much. The problem is, we are getting old, and it's time for the younger generation to take over.
Yes, we're both in our 80s now, so it's about time for the younger generation to take over.
All right, well, let's all thank Peggy one more time.